I never saw a cast. I'm online there. I'm online there. I just hear the echo of my voice, which is not the best idea. Let me find how I can remove that. Okay, I'm not completely sure. We'll see. Seems to work better here. Oh, maybe I have, yeah, no, I know where the audio is coming. I have probably opened Twitch myself, so means it works perfect. Ready to go. So as I did in the previous lives, I will follow the example of use the index Luke and run it on Yugabyte to see how it works. That may be the last one I will do on this topic and check the other chapters later. We will see about 1 hour and the previous time, so the past ones are available on YouTube, and we will look at partial and index filters there. Let me check where was all that. So that's the chapter I will look at, and the example schema. Sorry, the example schema for Postgres. I'm using the Postgres one. I think is this one. I think there is a table messages. Yeah. Okay, this one is okay. I will start. So that's a new table. Where is my terminal? I'm connected here to a Yugabyte cluster. This creates a table. I'm copying it as is. There is no primary key in Postgres. That's a heap table. In our case on Yugabyte, this will create an artificial primary key. We'll see if it's the best. In this case, don't really care because we are looking at indexes. While it is loading, I may have a look at my cluster. Here it is. So the table message is not there yet. Message there. By default, so Yugabyte has created a primary key because all tables have a primary key that are stored in the primary key structure in the LSM tree, and by default has split by hash on this key, which is a UID, so that's a good idea. And by default we run split per server, and in this version, which version am I on? This version we have already auto split, so if we load more than a few hundred of megabytes, it will start to split the tablets. But I don't think we have such a big table there with only 1 million rows. Okay, here it is. Getting back. So what we will see, we will create an index. Let me read what's the point here. So that's about partial indexes. So far we have only discussed which columns to add to an index. And with partial indexes, you can also specify which rows are indexed. The index is a subset of the table, subset of columns, can be a subset of rows and ordered differently. So there is a mention that Oracle has a unique approach to partial indexing. It's more a limited approach because Oracle actually doesn't have partial indexing. You can have partial indexing with partitions, and you can also play with the fact that nulls are not indexed, and that's probably what's the next section about. Oracle DB2 does not support partial indexes, but they can be emulated by excluding null keys. Okay, here we are with Postgres or Postgres compatible databases like YugabyteDB, and we can use partial indexes. So it's commonly used when you have a where clause with a constant. So here we have a colon processed that can hold the value yes or no. Could be a Boolean also in YugabyteDB or Postgres, but this example is generic. In Oracle, for example, you don't have Booleans. And the idea is to read all the messages that are not processed for a specific receiver. So the idea here, we have seen the last time that it can be a good idea to pass parameters to prepared statements. So for the receiver ID, we decide to pass a parameter, but for this one, we want to look only at the processed one. Could also be a view on top of it with processed messages, but here is the full query. So queries like that are very common in queuing system. The query fetches all unprocessed message. For specific recipient, messages that were already processed are rarely needed. So that means that you need an index to find the non-processed one, but you don't really care about the processed one. And anyway, you have a lot of processed one, and then an index will probably not be efficient. You can use partitioning if you want to restrict them. So the idea here is only to maintain the index for the non-processed one. We can optimize this query with a 2-colon index. So of course, if I run this query, I will prepare it. Maybe I have, I have all the syntax here, so I will just copy paste it. I'm preparing a statement. So I have my statement, sorry, just wanted to share, so prepare statement that I can then execute with something like this. So this doesn't really execute. This shows the plan, sequential scan. And as I did often, let me just paste what we have done in the file so that I keep track of it. Yeah. And I have my, I prefer to do some explain costs of to be less smaller widths and analyze. So this executes it and shows the execution plan, and the table is quite big. So this takes time because it is a sequential time, sequential scan. I have also my 2 functions to show some statistics. So the difference between the cumulative statistics about the YugabyteDB seek and next. So sequential scan, a lot of seek and next. Because I have multiple columns, then it has to read everything. So the idea then is to create the best index for that, which is this one, I guess. So we can optimize this query with a 2-column index, the 2 columns that we need, the receiver and the processed flags. Let's create it and talk why it is creating. So the advantage of putting receiver first here is that I can query on the receiver whatever the processed flag is. But we have seen in previous cases that with Yugabyte, and that's different from Postgres, with Yugabyte, we have the equivalent of index skip scan. So it's also possible in this case to put processed first. You can look at it. I think it doesn't make a big change because with process first, even if I query for receiver equals something, it will check the value n and then the value yes. So it's like looking 2 times into the index. That will not change a lot. So here the index is created and then running the same. So I have a snap reset, which is better. So execution plan now is an index scan, which is what I was expected. I think it is okay if I reduce the font size. To get a full width of it. Let's run the same. Yeah, so index scan, and we can see that it's not an index only scan. So going to the index, which is message to do, is fast. Just 1 seek to get there. 1 seek because we have first the receiver directly. We go there and retrieve all the rows. We have 100 of rows. But from this index, we have to go to the table. And that's something that will be optimized on Yugabyte. For the moment, for each row, it will get to the tablet. So that is a seek. We can see them there. We can see even more because there are multiple columns. But you can expect for 100 index entries, you can expect 100 RPCs to the tablet, which is not the optimal way to do it. But it's not really the topic here. We already have seen how to easily resolve this with a covering index. Why here I don't have an index only scan? Because the message is not in the index. So to get something fast with that, we can avoid the access to the table by adding the message in the index. The index it will be larger, but you gain a lot in the execution when you read many rows. If you read only 1 or 2 rows, you don't really care. So that's the most basic index we can see. But now we will see the partial indexing. So I will create it and talk about it. Of course, I cannot use the same name. I can rename it, but I don't really need the other one. So drop index message to do and creating this one. So the index, and then I will test something that I would like to test for the fun. So the index fulfills its purpose, the first one, but is too large. It includes many rows where we don't need an index access. All the rows with a yes, we don't really need an index for that, so it makes no sense to store the index. They are probably not updated, which means that it's not in the maintenance of the index that it causes problems, but we just don't need to store that. And this is where we create the index there. And if I run again my query, I see something that is very, very similar, because the activity on the index is the same, going to a specific row. It's just that the index is smaller. Here, with a small table, you will not see the difference, but a small index means that it will probably stay in memory. The first level of the LSM tree used by Yugabyte storage, first level is a mem table and stays in memory, and then you can expect, like for this table where you receive messages, the non-processed one, if you have 100,000 of them, they will probably stay in memory, and that will be really fast for a queue. Very similar to an in-memory database there, except that there is still RPCs to go there, and it is protected by write logging. So that was the point. We don't see it, but we index only that. The index only contains the rows that satisfy the where clause, and really easy with a where clause. And the index is very small. We will not see exactly the difference there. Can check it, but the size of the table, message, well, the size of the table is I thought I had the size here. So the size of the table is about 300, and for the index, it's probably very, very small. Where yeah, I will find index of message. What was the name of the index? Messages to do. Okay. 0. 0 is a file. This means that this index stays in memory. And it can stay always in memory. It is protected by WAL files, but it stays in memory. Okay, let's see what we have there. Index is very small. It does not contain all messages. And now you can also, so I have two things to test that are not mentioned there. The index is small, which means that if I create a covering index, includes message, the other column that I need, I add this column that may be large, but on an index where I don't have a lot of rows. And then I really shape the index for my query. I have all columns needed and only the rows needed. And finally, with an index that it's probably not so large, Coming back there, message to do. So this still fits in memory with an index on the wall table, an index only. It would have been the same size as the table, so in hundreds of megabytes. Here, this index is still very small and stays in memory, and is the most optimal one I can have because it's an index only scan, reading only the index. So this is small to maintain. The only thing is that when a new message will arrive, it will be stored in the table and in the index because it will be at process equals no. And when it will be processed, probably it will be updated. So maintain the table and the index. But then I have a structure that will store my queue. This is like a queue and maintain it in memory. So that's really efficient. I wanted to test something else, but I don't remember what I wanted to check here. But that's fine for that. So the message that is always the message I have in general for all databases. You shape the index for your queries. So here I have only one query. You can have indexes to serve many queries. So then you will shape it for multiple kind of queries. But that's really the thing. The most efficient queries will do an index only scan on an index that holds only the rows that are interesting. There is no reason to index rows that you will not query by index. And in this case, think about it. When we will process messages, we will update the processed flag. Let me show. Oh, sorry. Select star from messages. Maybe there are a lot. Where, yeah, I have. I want to show the results, so sufficient, yeah, okay. So I have 100 rows here with processed equal no. When I inserted them, it has inserted it in the table and in the index. And with all columns because I have a covering index. But this is just happened in the mem table, so that's fast. When I query it, I go only to the mem table of the index, so that's fast. And then when I process it, I will update this column processed from no to yes. And this will store the new version in the table and delete the index entry. If I had a non-partial index, it would be deleting the index entry and adding a new one for the new value. But here, the new value is not indexed. So this is also a way where you reduce the maintenance of the index. Those things are important in all databases, even more important in a distributed database. Nulls in database, this one is easy. Oracle is a bit special. It doesn't index null entries, but we don't really care about that in Postgres and YugabyteDB because nulls are indexed, which means that you can use an index for is null predicate. And if you don't want to index the null entries, that's easy. You can create a partial index where you just index the non-null entries. So you have all choices in Postgres and YugabyteDB. You have only workarounds with Oracle. So those are the workarounds. in Oracle, where actually, because that's quite funny, because an index entry will not be there if you have only nulls. You index the value in Oracle plus a constant, and then the entry is never null. You just add one byte, which is not a big problem. It's just dirty, but Oracle never implemented partial indexes. It's not a big deal. You have workarounds. This page is about not null. So if this is about Oracle, I don't really care anymore. I mean, sorry, I've been working a lot with Oracle. There are some features that I miss and I work around, but other new features I discover in Postgres and YugabyteDB. So this is the same kind of index, removing the null. This is again about null constraints that are special in Yugabyte. Let me just check. To index is null condition. Yeah, that's about Yugabyte, about Oracle, and we don't really care about that. Next chapter, emulating partial index on Oracle database. You read it if you are still on Oracle. You don't care if you are on Postgres or YugabyteDB. Next chapter, obfuscated conditions. The following section demonstrates some popular method for obfuscating conditions. So this is where clause I phrased in a way that prevents proper index usage. Okay. That's again about Oracle. I think it has to do with implicit conversions. We have seen that if you apply a function, an expression, or a function on a colon, you need to index the results in order to have index access to it. So the solution is function-based index. You create an index on trunk of the date, for example. The query uses date format. Yeah. MySQL has some strange things. We don't really care here. The following example shows implementation of the function quarter beginning and quarter end. So this is an example where you create a function and use this function in the query. Okay. Numeric strings, just avoid it. Huh? This also mentioned that this is an example with Oracle. If you pass a number as a character, you may have implicit conversion, and when you have implicit conversion, you have like a two-number function applied on it, and then if you want to index it, you need to index the result of the function, but just don't do that. Use the right data type. Combining colons. Concatenated index is very simple. There are a lot of names for that. Compound index, composite index, concatenated index. You can index multiple columns, and it's really as if you have the values one after the other. Not really relevant. For us, this is MySQL function-based index is not an option. I don't know exactly which version of MySQL doesn't support function-based index. We have all possibilities with YugabyteDB as it reuses the Postgres layer, so all those features are there. Smart logic. One of the key features of SQL databases is that the support for ad hoc queries. New queries can be executed at any time. So if you have queries that are executed a lot, better to have parameter and prepare them, but at any time you can run a query and the query planner will find the execution plan for your query. But from a program, it's quite inefficient to use dynamic SQL. First, because if you build the SQL statement by concatenating string, that will be more difficult to find it in the code. But also there is the idea that it can be slow. It's not really. And anyway, a lot of queries in Postgres are parsed each time because we don't have a shared pool for the cursors. Yeah, this is what Marcus mentions there. The big problem with dynamic SQL versus static SQL is mostly on databases that use a shared execution plan cache, like the commercial databases, most of open source databases. Just prepare statement in the session, but do not try to share it among sessions. So this is an example with bind variables. Yeah. With those databases where you prepare the statement, you may be tempted to prepare very generic statements. This is an example for an application where, for example, you have a multi-criteria screen where you can search with a subsidiary, employee, upper last name, and you provide one or all of them. And then many applications which fear the dynamic SQL, building the predicates depending on the user input. What they do, they define one prepared statement to be shared, and with a predicate that says something like, if there is no sub ID, then just read all the rows. If there is one, then use it as a criteria. So that's very clever. It works in the logic. But the problem is that this is very difficult to index because the execution plan will be built before knowing the value. And as there is the possibility that it reads all subsidiaries, it will not use an index to access it. So in this case, it is probably better to have specific queries, build the queries from depending on which parameters are provided by the user. Building them by concatenating strings is not really easy, but you can use a framework for that. You can use, for example, Juke, which make it quite easy to build it with strong typing, but build it at runtime. I will not go into that. And yeah, examples are yeah, Postgres query plan cache works for open statements only, so don't really have this problem. Yeah. Let me check what we have later. Matt. There is one more class of obfuscation that is smart and prevents proper index usage. So obfuscation here is hiding the real predicates that will be used at runtime, and then the query planner, the optimizer, cannot define the right index. I will come back just for this kind of thing, generic queries. There is also a possibility which is not mentioned there. What I do in this case, if I really want to have one query, rather than putting or predicates, I will do the different cases with union alls. And then at execution time, only one branch will be used. But the difference is that between two union all, you will have two query blocks, and one can use an index when the other does a full scan. If the OR stays like that, you have only one access to the table and cannot use the index or not. So this one, with some calculation, most database vendors just say no. Yeah, if you put this kind of equation, you know the arithmetic where you can transform it, but most databases will not do it. So your choice to write it in a way where you have colon equal something rather than something too complex. And then you do the math to define your query in the right way. And if it's complex expression, you can also create a function and index the function and declare the function as immutable, no, deterministic. Okay, I think I've covered most of the things I wanted to look at. So that will be short today. There are some chapters about performance. I will just go through it. The impact of data volume. Sequential scan has to read the whole table. Index access has to read the rows that it needs. So that's a big difference. Big advantage of index access is that the table can grow. The performance of the query you're accessing by index will stay. The index access cost will increase when you read more rows. But then the user also can understand that if you read a 3 years history, can take more time than reading a few days, for example. In Oracle, but we have seen that also before. In Oracle, you see access when the predicate is used to access to a specific part of the index, so efficient indexing. Filter when the filtering may be done from the index values, but after accessing to the rows. In Postgres and Yugabyte, you see something different. You see index condition, like I probably add somewhere. Index condition means that the condition is either on the index access or filtered just from the index information. From it, you don't have the same thing as with Oracle access and filter. So be careful, even if you see the whole predicate in index condition, maybe you are reading the whole index and filtering later. Just important to know it. What do we have here? Yeah, we have seen that, and I've been talking about the performance while doing the example, so this is also why I don't really need to read it again. Always look at the statistics. I'm using my little script here to gather the, let's see them, the seek information. We will have soon those kind of information getting back to the execution plan so that you don't need to query it outside of the execution plan when doing unexplained analyze. For the moment, we still have to do that because we just show the execution plan from the information that we have at Postgres layer. Those statistics are in the distributed storage layer and need to be returned to the upper layer to display them. Okay, response time throughput. I will not go there for the moment on this. And then there are chapters about join operations. This is very important, but I will probably look at that later. And by later, I mean after a few releases of Yugabyte. And the reason is that for the moment, nested loop is not really optimal because when we get from the Postgres layer, when we get index entries, there is no optimization to batch the access to the table. So today, the optimization for those either access by index or nested loop is really on the indexes that you provide to avoid this n+1. Actually, currently in Yugabyte, we are doing this n+1 because of the 2 layers. This is the idea of Yugabyte, plugging Postgres and then optimizing later what needs to be optimized for a distributed database. But at least we have all features. Okay, what? So of course we have hash joins, and this is efficient because all rows are retrieved to build the hash table, and this works in the Postgres layer, which means it will take memory, but as you scale the connections, you can connect in many nodes in Yugabyte. Just be careful on the memory, but you can scale it. You don't have the same limit in using memory as in a monolithic server where many connections using a lot of memory will probably use too much of it. And sort, merge, join. I will do something about join methods, probably in the same way I did it for Oracle, looking at each join method. But those are things that will be optimized soon, so probably better to do it later. Those are things I've already covered. Those are databases with heap tables. And then clustering factor is something important. How rows are scattered when coming from an index. In Postgres, it is the same, but in YugabyteDB, we store all rows in the primary key, and then we don't have this clustering factor when accessing by the primary index. If you access by the secondary index, you try to cover all the columns so that you don't have to go to the table, and then you don't have this clustering factor issue. Okay. Avoid select star because it will retrieve all columns that maybe you don't need, and that may prevent an index-only scan. Limitations of B3. We don't use B3s. we use actually something very similar to index organized table and clustered index, storing the table in the index structure, which is something that you cannot do in Postgres. Postgres uses only heap tables. Oracle has the choice. MySQL InnoDB uses only clustered index. DB2 DB2 has also heap tables, can be reorganized. But SQL Server has both, but the default is usually clustered. For OLTP, where you very often access by the primary key, clustering as we do in Yugabyte is probably the best. And it is clustered, but it is also distributed. So first you distribute, and then within each partition, shard, tablet, rows are all together. Okay, next is indexing for order by. We have seen that also. The query planner is aware that a result from an index scan returns rows orders and then doesn't mean more sort operations. So in your query, in your SQL query, you still put an order by because you declare that you want the result order, but the query planner will optimize that. This is something I will cover also probably later, or maybe just I will finish on this one because this is also something that I wanted to check and show. I will see the table I have here. Was message, huh? Messages. So I have an ID, I have a receiver. How many receivers do we have? Select receiver. I copy paste will be easier. Consta from messages group by receiver. Will be a full scan. What I want to do is create an index on a number, a range index, so to show ascending and descending one. Okay, I have many values for receiver. That's perfect. So I will create index message receiver ascending on message. The receiver if I leave it like this, by default, the first column is hashed, and this is not what I want. I want a range index because I will have range scan. So I will create one ascending. And we'll create another descending. And my goal will be to show what happens when I query that was the ascending. Let's create a descending one. When I query select, I will count from message where receiver ID between. So this is why I went to the range index. With hash, you can not use the index to do a between, and I don't know, between 10 and 100. And yeah, let's run that. I've created both indexes. Of course, you create only one, but I've created both to check how they are used. So we have index only scan, reading a lot of rows, 900,000. It has seek into 900 places, so that's probably the different values, and then add some next, which means that you seek and then you read what remains. And I want to compare, I will use int to compare the usage. So int index only scan table messages index. So here the query planner has chosen descending one. I will run the same, forcing descending one, so will be the same. Okay. The descending index. And now running the same query using the ascending index. So the time first, even if I don't really like to look at the time. Descending index, about 900 seek, about 1 million next. This for 6 seconds. A bit less for the ascending one, but the same number of seek. So here we can say that it doesn't really matter. Ascending or descending is the same to get the different values. Yeah, this is ascending, I was checking. Okay. I'll try something else. Let's say we have an order by receiver, and I will query only receiver. With the ascending index, very similar to what I had when counting. And with the descending one, I'm testing something where I don't really know if there is a difference in this case. What I've read from the code is that when you read in ascending order from an ascending index, you seek next, seek next, seek next. And when you read from in ascending order from a descending index, you will have to seek, you go next, but then you have to seek back. And yeah, that's actually what I'm seeing there, perfect. So here we see the difference. It didn't make sense without an order by, because I don't care about the result, so I can use one or the other, and the result will be returned in the order of the index. Here, with an order by, we want to use the index to get the results sorted. Neither of them has a sort operation. Let me try to put them at the same. Yeah. I have an order by for them. I have no sort operation. So it is read in a way where the result is sorted. But when I order by, where was it? When I order by in ascending order and I read from an ascending index, those are just seek, next, seek, next, seek, next. So you see very few seeks. They are just getting from one value to the other because I have many rows there. But if I still want an ascending order when reading from a descending index, then you have those seek backs, and you see them here. And it has a cost that we can see in elapsed time was 6 seconds, and now 19. So the order of the range index when you define ascending and descending, you should think about what is the order that will be probably be used by the users. Probably you can guess that from the data type, for example, if you have, or the colon. If you have a colon on a date, there are many queries who want the latest one first, and then maybe creating the index with descending is a right choice. But don't forget also that order by default to ascending, so if you have to default to something without knowing, probably better descending. Here, if I run the same, so forcing descending index, asking for descending order by, then this should be the same as we had before the 6 seconds, and I didn't count the 6, but the same as ascending with ascending. Here I didn't show the cost. I will run the same with the cost on. I want to see if the query planner is aware of that. I'm not really sure that we have implemented it because this is specific to the storage. I don't even need to execute it. I can. I'm running on a really small cluster and do not take the performance as the best performance possible. I will just explain. So an order by ascending with an ascending index. What is the estimated cost of that? 5.15. See it there. What if I run now the same with a descending order, where I know it is more expensive because of those seek backs? Was it a typo? I'm forcing an index that doesn't exist. So finally it does something else and assigns high cost. This is the way Postgres and Yugabyte uses ints. When you int something, it doesn't really force it, it just puts the highest cost for the others. But if it's the only access, it's done. So I wanted to compare 5.15 with 5.25. This one is more expensive because I have the SIG back and cost is different. That's the most important. You don't need a big difference because everything is the same. I have same data. I have just a little difference on if I don't have a lot of different index value. You don't see the difference. Here I have a lot. So you see this difference there. So the query planner is aware of it, which means that if you want, you can do as I did with 2 indexes. Of course, reminder that the more indexes you have, the more maintenance it has to do on DML. But if your goal is really to optimize for all kind of queries with order by ascending or descending, you can define both indexes. And it will choose the right one. Means that with an order by ascending, it takes the ascending index. With order by descending, it takes the descending index. So the query planner is aware of it. You can create both, of course, if you want to favor fast queries, the most optimal queries, and don't really care about the maintenance of the index on tables, maybe that are not changed very often. Okay, that's all what I wanted to look at, and I think I may change my mind, but I think that for the moment I covered what I wanted to cover from use the index look. I really recommend all Marcus Winand content, so this website, which has been translated in many languages, but there is also a book, stickers also, but here is the book. So this book has the same and even more. Very well explained, a lot about indexes, but not only about indexes. This is the book I recommend to anyone, any developer who wants to learn about SQL and write efficient SQL queries. And if you follow the recommendations there, you will not be this kind of developer who thinks that SQL doesn't scale. Because when you do things correctly, correct indexing, correct data model, and correct querying, you will see that SQL databases can do a lot. And the advantage is that they can cover a lot of different use cases where no SQL databases are really specific to specific things. Okay, see you next time. I will put the recording on YouTube, and you can look at it if you want to understand. For example, if you read Marcus Winand book and see what is the same and what is different on Yugabyte, then you can follow those videos. Have a nice day, and next time I may do something that I have in mind with something like learning SQL, the very basics, but I will see when I do that.